In this lecture, we're going to turn our attention to the fate of high mass stars, what their evolutionary sequence is after the main sequence. By high mass stars, we mean stars greater than roughly 8 solar masses.
Now, continuing a technique we introduced last time, let's compress a massive star's life into one day and go through the various stages. So again, the main sequence life of a massive star is much the same as the main sequence life of a low mass star. It spends its time burning hydrogen into helium in its core. Of course, it takes a lot less time to exhaust its core's supply of hydrogen than a low mass star, and so its main sequence lifetime ends sooner. It is still, however, 90% of the overall lifetime of the star. So for a massive star, its life on the main sequence and its expansion to a red giant takes about 22 hours, 24 minutes. Okay, so at about 10:24 p.m. at night, on the day that is the life of the star, that's when the hydrogen burning phase ends. So at 10:24 p.m., that's when helium ignites. For a 25 solar mass star, in real time, it takes about 7 million years. Okay, at 10:24, helium ignites and starts burning to carbon and oxygen in the center. You have the ashes of helium surrounding the helium-burning core, and you have a shell of hydrogen that is burning to helium. This red giant phase takes 1 hour, 35 minutes, and 53 seconds, give or take, and therefore takes us to 12:59 p.m. and 53 seconds. In real time, this phase of the star's life takes about 500,000 years. For a 25 solar mass star. Okay, what happens next? Well, for low mass stars, that's when the story ends. The outer layers just expand and drift off. The core of the star never heats up to temperatures sufficient to ignite carbon and oxygen. For a high mass star, the gravity is enough to compress the core and increase the temperature to where carbon can be ignited. So we get carbon ignition, and carbon starts burning to neon, sodium, magnesium, and oxygen. Around the carbon-burning core, you have carbon and oxygen ashes. Around that, you have helium-burning shell. Around that, you have helium ashes, and around that, you have a hydrogen-burning shell. Again, outside of all of this, you've still got the hydrogen atmosphere of the star. Carbon burning takes about 6.99 seconds and takes us to 11:59 p.m. and 59.99 seconds. So we are 100th of a second away from midnight, the end of the star's life. In real time, this corresponds to 600 years. Next, neon ignites and burns to oxygen and magnesium. This is surrounded by a shell of neon, sodium, and magnesium ashes, which is surrounded by a carbon-burning shell, which is surrounded by a shell of carbon and oxygen ashes, which is surrounded by a helium-burning shell, which is surrounded by a shell of helium ashes, which is surrounded by a hydrogen-burning shell. You see, the star is beginning to develop what astronomers refer to as an onion skin-like structure. There are many shells with different chemical compositions and different types of burning going on in each. Neon burning takes about 6 milliseconds in our one-day lifespan, so this gets us to 11:59 p.m. and 59.996 seconds in our day. In real time, the neon burning phase lasts about a year for a 25 solar mass star. Next, oxygen ignites and starts burning to silicon, sulfur, and phosphorus. Oxygen and magnesium ashes sit in a shell outside that, and you have the rest of the onion skin-like structure outside of that. Oxygen burning takes about 3.97 milliseconds, which takes us to 11:59 and 59.99997 seconds. Oxygen burning in real time for a 25 solar mass star takes about half of a year. Next up, the silicon ignites, and that starts burning to cobalt, nickel, and iron. Outside of that, we have the rest of the onion skin-like structure. Silicon burning takes about 0.03 milliseconds in our day's lifetime of the star, and that is the final 0.03 milliseconds. This is the final act of this star, and that corresponds to about 1 day in real time. This is meant to say 1 day, apologies. So for a 25 solar mass star, the silicon burning phase of its life lasts an actual day, a real day. So you can see that these final stages of a massive star's life happen very, very quickly by astronomical standards. We're used to things taking billions of years, or millions of years at least. These final stages happen in a year and less. As we saw when we covered the basics of nuclear physics, when you end up with iron, you cannot extract any more energy from nuclear fusion reactions. So that is where nuclear fusion ends. What happens next, we'll explain in a couple of lectures' time. So what do these evolutionary tracks look like? Well, if you take, for example, a 10 solar mass star, then it evolves off the main sequence and onto the subgiant branch, and then the red giant branch, down onto the horizontal giant branch and onto the asymptotic giant branch. And then it will repeat the same thing again. Once it ignites carbon and oxygen, it'll come back around onto another horizontal giant branch, another asymptotic giant branch, until it ignites neon, and then we'll keep on going through a series of these horizontal giant and asymptotic giant branch. Now, because after carbon and oxygen burning, the rest of the stages of the massive star's life take so little time, we actually rarely see stars during those stages of the life. Most of the stars that you plot on a main sequence will be on the first go-around of the horizontal and asymptotic giant branches. So this is a sketch of where you're likely to see stars after the main sequence evolution, after they have for various masses. And what I want to note at this point is this orange band here, which is labelled Cepheid. Stars that pass through this region here, as they move along the subgiant to red giant branches, pass through an instability region. And it's a good job they do, because that leads us to the next rung on the cosmic distance ladder, which we will come to in the next lecture.